logconference.org. You click on Program, click on Tutorials, and then Day 1 Tutorials. There should be setup instructions for you to follow along.
Here. Yeah. I need to speak here. I can speak very loud, I think. Okay.
Hello. All right, welcome to the tutorial session for Relational Deep Learning Foundations, Advanced Methods, and Hands-on Development. Those of you who are joining us online, you are most welcome to engage with the organizers and each other in the tutorials discussions Slack channel. So this session will be 3 hours long. There is no other event following this session, but please do end on time. Thank you. For those of you who are unable to join or who would like to rewatch the session in the future, the tutorial is being live streamed and saved to our YouTube channel. So be on the lookout for that. And without further ado, I will hand it over to our tutorial organizers.
Yeah, maybe. Yeah. Hello, everyone. I'm Harilaos, and together with Vijay and Andy, we'll present this tutorial about relational deep learning. We'll discuss about challenges, foundations, and next generation architectures. So hopefully, by the end of this tutorial, we will have convinced you that relational deep learning has the potential to reshape the way we think about data science, and also opens up a bouquet of applications and also opportunities for innovation in graph machine learning. I was asked to speak loudly, so if there is a problem, someone cannot hear me, please let me know. Oops. Okay, awesome. So yeah, this tutorial is joint work with my friends and colleagues, Vijay Prakast Vivedi, he's a postdoc at Stanford right now, and also Andy Huang, who is a postdoc at Oxford. And of course, it could not have happened without the vision and also the support of Professor Michael Bronstein and Professor Jure Leskovits. So the outline of this talk, so the first half an hour, I will try to introduce you to the basics of relational deep learning. Then I will hand it to Andy, who will talk about graph machine learning model and will focus more on the temporal aspect of relational databases and how to process and handle these temporal aspects. Then Vijay will talk about frontier and next generation architectures, next generation graph neural networks, and next generation transformer. I will take the microphone for 15 more minutes to discuss about recent advances in foundation models for relational deep learning, and then we have a hands-on collab notebook that we hope you enjoy, and you will have, you will get your feet wet with relational deep learning models. Yeah, so motivation, I like to start this, usually when I talk about relational deep learning, I would like to start with this cover of The Economist. So it's an old cover, it goes back to 2017. And what it says is that the world's most valuable resource is data, even more valuable than oil. And if you think about it, this cover might be right, because right now we're experiencing the Gen AI era, where all these amazing models, large language model, vision models, have been trained with lots and lots of open source data. However, the caveat here is that these data are public and open source. So, arguably there is an even more interesting and valuable and, important type of data, and these are private data that can be found in modern data warehouses, in modern databases, in enterprise, in industry, and these are data that are usually stored in tables, and these tables are interlinked via primary foreign keys. And there are several examples where this data can be found. For example, in e-commerce networks, certain type of information can be stored in tables of customers, tables of items and tables of orders that connect customers and items. So you see here, we have different tables, and these tables are interlinked via primary foreign keys. Or you can find such data in finance, where you can have tables of accounts, tables of clients, tables of loans, and tables of orders. Again, these are, it's a relational database. It's a database with multiple tables interlinked with primary foreign keys. And same idea, you can find data in hospitals or clinical trial data, where you have tables of diagnosis, procedures, patients, and again, these tables depend with each other, have dependencies between each other. Now, usually the way people are processing such data is to look at the relational database and try to answer some historical queries, to do some type of analysis. This is not what we're doing in this tutorial. So in this tutorial, we're going to focus on predictions, on forecasting over relational databases. And let me give you some examples. Let's consider an e-commerce, again, database. And then we are interested in answering several types of predictive queries. For example, which products will a user purchase in the next 7 days? Why is that interesting? Because that's a recommendation task. Or we might be interested in saying, okay, will a user remain active or inactive in the next 3 months? Again, that's a very interesting question, because suppose that we are able to predict such a thing, we might somehow perform some actions to avoid user inactivity. Or we're interested in saying, what will be the total sales for each product in the next month? Why? Because we might be interested in optimizing inventory. Similar things in a financial database. We want to answer predictive queries or predictive tasks of type, what will be a good loan outcome, or what will be the total number of failed loans in the next year. Finally, again, for the example of a relational database in a hospital, in clinical trial data, it's very important to be able to answer, to make some predictions. For example, whether a patient will return if discharged from a hospital, or which hospital admissions have the greatest risk to life in the next day. Why? Because somehow we have some confidence on whether or not it is safe to allow a patient to leave the hospital. And, of course, we are not the first people who ever thought to answer predictive queries or tackle predictive tasks over relational databases. However, building machine learning models over relational databases is kind of brittle. And the reason why it is brittle is because there is an impedance mismatch in the way data are stored and or naturally organized, and the way data are somehow processed in order to be able to be ready for machine learning models. To give you an example, let's consider that we have the task of user churn. So we're trying to answer user inactivity over an e-commerce network. So this e-commerce network, or this particular example, has 5 different tables interlinked via primary foreign keys. So the way usually we go over such predictions, so there is a human data scientist that massages all these 5 tables or joins all these 5 tables into a single one. And then we have a single table, and we can use our favorite machine learning model, whether this is, XGBoost or some random forest, or the recently proposed foundation models for tabular data. So, and we are good to go. So overall, we want to do some feature engineering from the raw data from the relational database to transform the data into a single table. And this is a suboptimal approach, and the reason why it's suboptimal is because it's very laborious for the engineer and it requires time in order to do all this feature engineering and transform the data into a single table. On top of it, we might have some loss of predictive signal. So we go from multiple tables into a single table with human decisions. So we don't really know if we include the right features that somehow play the most important role for a potential future prediction. And also it's kind of complex to maintain because these databases most of the times are updated over time. So we have new data coming in, and then we need to go over the same process of feature engineering and transform the data into a single table before we apply a machine learning model. So the question that we're trying to answer today is, can we actually leverage this data without going through this laborious and somehow time-consuming process of feature engineering? So we want to somehow build machine learning models and machine learning algorithms that can process the data in their natural form. And if you think about it, that's somehow the natural path for such a data modality. And this is similar to the evolution of computer vision. So at first in computer vision, we were designing filters, or we were computing some features and then apply some predictive models. Similar, but in these days, I mean, also few years back, we started with convolutional neural networks processing data end-to-end, or these days with vision transformers. So we want to go through the same somehow process in the relational database domain. So yeah, overall, we want to generalize deep learning to relational databases. And this machine learning paradigm, we will call it relational deep learning, and we will abbreviate it by RDL. So the idea is that we have the raw data, tables plus primary foreign keys, and we want to have a machine learning model that operates directly on the data to make predictions. Now, if I had to define what RDL is, there are these three bullets. So it's end-to-end deep learning on relational tables. So these are databases. It works directly on relational tables, and there are no transformations and no feature engineering. And it casts the predictive tasks as graph representation learning problems. Of course, we are in the age of Gen AI, and have seen the amazing success, amazing advances of large language models. So it's very natural for someone to ask, okay, what if I use large language models for that? What if I serialize the database? I somehow prompt the LLM with some part of the database and the predictive task, and ask the LLM to answer this query or this particular predictive task. And actually, people have tried to do that, and that's exactly what they did. So they serialized the database and they prompt an LLM. However, this is how the prompt looks like, and it doesn't look very, very good. So, of course, here, it's not a beauty contest. So if it works, and we're fine. However, when it comes to this type of approach of serializing or textifying relational database into text or into a sequence, then that's not very natural. So LLMs are not actually trained to understand and effectively learn from this relational or complex structure of databases. Another limitation is that usually what happens is that you cannot process the whole database because you are limited by the context size of the large language model. And of course, as we will discuss later, it doesn't work very well in practice. So here I have some results. These results are some binary classification tasks. So we have different data sets, different tasks here. So this is when you do in context learning with Llama 3.23 billion. And this is a graph neural network approach that we propose. You don't need to bother about the details. But the point I want to make is that there is a huge gain if we design specialized models that are able to somehow capture the inter and intra-table dependencies of relational databases compared to, let's say, using large language models for making the predictions. So, and this is binary classification. By the way, if you are interested in regression tasks, large language models fail terribly. So they don't even produce results that are better than some naive baseline. Yeah, so we'll discuss about large language models and of course, different models later. So stay tuned. Now, hopefully, so far I have answered the question of why. Why are we interested in somehow building this new machine learning paradigm, which we call relational deep learning? Now I'm trying to somehow tell you how we are going to do that. And the insight here is that a relational database is a graph. So again, let's consider an e-commerce network with users, sales, and products tables. Now you can consider different users being different nodes in the graph, or different products again being different nodes in the graph, and same for sales or transactions. And then there are some connections between users and transactions and items. And therefore we have a graph. I'll go into more detail later. Now, what is super cool about using let's say somehow the graph machine learning framework or the graph machine learning language is the fact that it's so rich that somehow it can model many predictive tasks or many significant predictive tasks into graph learning problems. For example, user churn, user inactivity, or user lifetime value, or next best action can be cast as a node level task. So user churn can be cast as node classification, whereas let's say user lifetime value can be cast as node regression. And then there are some other tasks such as product affinity or recommendations, which can be cast as a link prediction task. And we can have graph level or subgraph level tasks, for example, fraud detection or money laundering. So the idea here is that, we have different tasks, different interesting tasks from a business perspective. We can cast them as graph learning tasks. So, the whole pipeline of relational deep learning goes as follows. We start with the relational database. We transform the relational database into a relational graph. Then we transform the predictive task into a graph machine learning problem. And then we build graph machine learning models, GNNs, transformers, foundation models, in order to answer such predictive queries. And this is what we're going to discuss today. So now, let me first tell you how you can transform the relational database into a relational graph. Now, there are two graphs that help us somehow describe a relational database. The first is a schema graph, and the second is a relational entity graph. Now, again, to be more precise, I will show you how we can do things using this e-commerce example of users, products, and transaction tables. And the thing is that, if you look at such a database, there is a transaction table, and this transaction table has different columns. There is a primary column, primary key column, which has a transaction ID. And there are, foreign key columns, the user ID here and the product ID. And then there might be some other features, such as the value of a transaction, this is a numerical feature, or the timestamp. And these are the columns of this transaction table, and different rows correspond to different records or to different transactions. And what is cool here is that we have entities, and the entities are the rows, or maybe the general users, products, or transactions. And these entities have different types of features: numerical, categorical, timestamp, text. You can have images or whatever else you can imagine. So yeah, so we also have some user tables. You can see here, this user table has primary keys, a primary key but doesn't have a foreign key. It has a categorical variable as a feature. Same for the product table. And these three tables somehow define the database. And as I said, rows will be later on our nodes. But we also need to have edges, and the edges are somehow, the edges are somehow guided by primary foreign keys. For example, here we have this table has two foreign keys, the user ID. So 51 here is a foreign key, but in that table is a primary key. So there is a connection between this row and that row. And again, there is a foreign key product ID in that table, which is a primary key in the product table. And that's how we can connect different rows in the database together. Now, if you like mathematically, a database is nothing but a set of tables, which we denote here as calligraphic T, and the links are defined as a Cartesian product between the set, the set of tables. as I said, there are two graphs that somehow allow us to describe and understand the relational databases. The first is a schema graph, which somehow gives us a high-level intuition or a high-level description of the data. And this high-level description gives you somehow the features or the columns that each table has. And also there is somehow the high-order connectivity. So which entities of which table can connect with which other entities of another table. But this is a somehow a high-level description of the database. So in the e-commerce network, we have, again, a table of products with their features, a table of customers with their features, and transaction which somehow connects products to customers. This is a very simple schema graph. However, in reality, you can find very much more complex schemas with tables with many features and multiple tables with complex connections. Such a table can be this rel trial schema, which we briefly discussed before and we'll also discuss a little bit later, or it can go as complex as this schema over here, which it comes from this Adventure Networks database. It can be found by this CTU database, and this is what happens. So, suppose, imagine that you are a data scientist now and you're trying to predict or to make predictions for a particular table. So you somehow need to massage all these tables into a single one. So, we are not going to have this problem because we are going to operate directly on the raw data. Yeah, so the second graph is the relational entity graph. I already gave you some idea. So we have a user table. Each row in the user table is a different node or a different node. And you have, in that particular case, 3 different node types. So we have different nodes which are users. We have nodes which are products. And we have nodes which are transactions. And users are connected to transactions. And products are connected to transactions. So this is a heterogeneous graph. And mathematically, if we want to define it, so we have a database, again, which is a set, this calligraphic set T, and then each table is a set of entities, V, that belongs to a particular element in the set of tables, and we have the primary foreign keys. The relational entity graph is defined such that the set of nodes is defined by all rows in all tables, so all the rows are nodes, and all rows in all tables are all the nodes in the graph. And then we have the set of edges, which are 2 entities. You can think of them as 2 entities or as 2 rows connected with each other. And these are, the edges of our graph, the nodes and the edges of our graph. Now, in the next 10 minutes or so, I will explain how we can somehow transform or cast a relational query, a predictive query, into a graph task, and then I will discuss about some data sets. So yeah, how we can actually define and describe predictive tasks in relational databases. The idea is the following. So we start with a task. Let's say that this task is user churn, so user inactivity, or maybe another task here can be how much will each customer buy in the next 3 months. So what I will do is I will look at my database. Suppose that for this particular database, I have data from 2010 up to 2025. So I will look at the historical data, and looking at the historical data can create labels. For example, let's say that I'm interested in predicting user churn. So I will somehow look at the activity of different users over the course of these 15 years from 2010 to 2015, and I'm going to create labels for each user given the timestamp. Now, after collecting these somehow labels from the database, we will create a table which will be called, we will call it the training table, and we can then connect the training table into our database. But the training table is particular for a particular, it's specific for a particular task. Let's see how this works. So again, the idea is that we are interested in user churn or user activity, predicting user activity in the next 30 days or in the next month. And what is super important when it comes to such tasks is the fact that they are temporal. So, or in other words, time is a first-class citizen when it comes both to relational databases and also predictive tasks on relational databases. So long story short, the customer label changes over time. For example, if I ask whether or not a user will be active in the next month, the answer might be different if I ask the question in January compared to if I ask this question in July. Why? Because user activity changes over time. And the second very important thing is that the database also changes over time. We might have new users coming in or users leaving the particular e-commerce network. We might have new features in our database or maybe extra information which can be modeled as a table. So again, the point I want to make here is that temporality is super important, and later on Andy will discuss more about that. Now, in order to define a task, we need three elements. The first element is the entity. For example, in that case, the entity will be a particular user or the user ID. We also need a label. In case of user churn, this is a binary label. 0 means active, 1 means inactive, let's say. And we also need the timestamp. So when do we ask this particular question? And given these three elements, we can somehow define a training table. And this training table is a special table containing the labels. Or in other words, it's a table that has three columns. The first column is the entity ID. The second column is the timestamp. And the third column is label, as I said, for user churn 0 or 1. Or we can have a multi-class classification label, or we can have a regression label. For example, user lifetime value, it's not a binary classification task. It's a value that we put in the label column. And so I think I made that clear. So time is a super important component for many reasons. One is time leakage. So when we make predictions, when we are building models, we should always make sure that we don't look into the future to make predictions for the future, because in that case, we have time leakage. So this way we can create this training table, and we can then connect this training table in the database. So here, this training table is about user churn. So we will connect this training table to the table of customers in this e-commerce network. So to give you one more illustration about how this table with the task look like. So we have these, let's say, different nodes which are users. We have nodes which are transaction, nodes which are items. And now for each user, we can have different labels. So this user, we say they churn in May 23, but then the label changes and the user becomes active in June 23. And similar idea, similar picture for this user over here. But for that particular user, we only have one record. We know that this user is active in June 23, and we don't have any other records about this particular user. Or for this one, we have more than two and more than one. So we have, we know that the user is active in April, inactive in May, and then again becomes active in June. So you can see that the label can change over time. And something also important, we have multiple labels for a particular node in the graph. And these multiple labels also have a different timestamp. So overall, we start with our database. We transform the database into a graph. We transform the predictive query into a graph machine learning problem. We connect all these things together. So then we have a graph. We have labels for the nodes in the graph. And we can develop different models, different graph machine learning models, such as graph neural networks or transformers to make predictions. So the next step for us is to discuss some different architectures. But before that, so a graph machine learning paradigm or different architectures do not worth anything if we don't have data to test our models on. And so I'll spend the next 2 or 3 minutes to discuss about some public databases that you can use. One is RelBench. It was introduced in EuresLab a couple of years back. And the idea is that RelBench contains different relational databases. It has data, task, and graph loaders for these different relational databases. You can use different frameworks. One of them is PyTorch Frame. So PyTorch Frame can encode different attributes, different feature spaces into a common space. And you can also use all the models that are in PyG. And finally, there is an evaluator to assess the performance of different models. Now, if we go to the details of the data sets, we have 5 different datasets in Relevance that span 4 different domains. So we have 3 commerce networks, 2 social networks, 1 sports database, which somehow has the results of Formula One over the years. And we also have a medical database, RelTrial. So in these databases have 3 to 15 tables, and also the tables have 75 to 41 million rows in the data, or maybe, yeah, all the tables have this number of rows, and the total number of columns can be up to 120. Or in other words, the highest feature space that we have in Relevance is 140. And the time span is from 2 weeks up to 55 years. I think the F1 database should be 55 years, if I'm not mistaken. Also, there are many predictive tasks that we have defined that can be cast either as entity classification, meaning node classification, or node regression, and we also have some recommendation tasks. Overall, 30 different tasks in Relevance. Now, if you are interested, it's very easy to install. You just do pip install Relevance, as we will show next, maybe towards the end of this tutorial. And you can check this website if you are interested in getting started with Relevance. There are also some other public repositories. One is the CTU Relational Dataset Repository, a very interesting database, very interesting set of datasets, many databases, usually a single task, classification or regression over these databases. There is also 4DB Infer by some Amazon researchers and some other collaborators. And that's also a very interesting database that you can check. And also recently, there is one released from SAP. It's called SALT. And this SALT database is also included in the Relevance repository if you are interested. So that was the first part. I can take a couple of questions and then I will hand it on. Any questions from Slack? Okay. What's the question? Okay, so yeah, okay, maybe we can take that. We can respond. It might take more time than we have. Okay, cool. So.
So my name is Andy. I'm a postdoc at Oxford, mostly working with temporal graph learning and graph learning. Thanks to Carlos for the great introduction on the first section and motivating the problem and the setup and how we get from tabular data into a graph machine learning problem and task and setting. Now we'll look at how do we actually design some models to work with all the challenges in working with relational deep learning. So as we see before that, so we have converted to a graph, the relational entity graph, and then we also take some temporal sample subgraph. So we'll see that in a bit. And then we have a representation learning model that we have, such as GNNs, and then we can use that to do our forecast on some task, right? So basically, which models can we deploy, and then which type of model can handle all the challenges? So in this section, I will talk about three different components. The first one is just the standard GNN. So I will do a quick section just as a refresher on that. And then I will talk about the heterogeneous GNN. So how do we extend standard GNN working on homogeneous graph into heterogeneous graph? And then for the last part, I will put my emphasis on temporal GNNs. So how do we handle the temporality that is natural and very important in RDL? So in the GNN section to start, so the goal of a graph neural network is to learn from the graph structure, and the graph neural network is using the graph in a very explicit way as well, right? So the objective is to learn an encoder that maps the node in a graph into low-dimensional embedding vectors. And this representation of node embedding vectors or latent vectors of nodes in a graph give us flexibility to perform all kinds of tasks that I've seen in Carol's presentation on node level, link level, graph level. So for node and link level, you can just take one node or two endpoints of a link, or you can just do a pooling over the entire graph. And you can do many different type of tasks once you have a representation of nodes on the graph. Right? And then the idea of a GNN layer, as you may are very familiar with, is to have this two-step process. So the main intuition is to compress a set of vectors from the local neighborhood of your node into a single vector, a single hidden vector at the end. So it's a two-step process. So you have a message function, which checks which messages that you want to pass along. And then you have the aggregation, which then does a set operation on the messages. Right? So we have seen like GCN as an example. So where we have the node embedding, and then we have the big bracket is the activation. But before that, we will look at what are the neighbors of the node that I'm interested in. And then we also perform a normalization. So this is more specific to GCN on the node degree. And then we have a weight matrix that multiplied by the hidden embedding. Right? So in the message part, each neighbor is normalized by the node degree. Right? And then when you are doing the aggregation in the GCN setup, you will simply just sum over the messages from the neighbors. And then here, there's also a step of the self edges to include the node representation of itself, which is important to preserve that information as you do propagation. Right? And then we have more advanced models that try to learn the importance of different neighbors in the graph, right? So here you want to learn attention. So then we get to the GATT model, the graph attention networks. And then here, the key idea is you have the alpha, which is the attention weight. And then this attention weight will learns to dynamically change the importance of each of the node's neighbor based on the task, right? So this allows the model to ignore some of the neighbors' messages while focusing or zooming in on some of other neighbors' messages. So this makes the learning more flexible, right? So that's a quick recap on the standard GNN. And now I will talk about heterogeneous GNNs. So on the heterogeneous GNN side, we want to model the challenge of the data heterogeneity. So so here you have different type of nodes and relation types, right? So we want to extend a model such as GCN to handle heterogeneous graphs with multiple edge and relation types. So so how do we go about this? So we start with a directed graph with a single relation, and then we see from before that a GCN will basically pass messages along the direction and doesn't really care about the type of relation that is, because there's only one type of relation on the graph, right? And then to extend to multiple type of relation, for example, now you have a complex purchase network where you have the buy operation, you have the review relation, and also something like a wish list, right? So here, the key idea is to use different set of neural network weights to represent different relation types. So so here we'll have one set of weights, WR1 for the buy, and then the WR2 for the review relation, and then WR3 for the wish list type. So now with that learned, then we can look at the messages, and then when we are propagating them, we'll use the type-specific weights to multiply by the node embeddings, such that we're aware of the type of the relation. So yeah, so here's more similar example to before, and here's the equation. So basically, instead of a single sum like before, now we are looking at all the different type of relations. So this outer loop now is the different types of relations that you have, and then you check for each of the relation, what are my neighbors, and then for these neighbors, you would aggregate similar to what we have with GCN, right? Also, in the same sense, you need to normalize by the relation type as well. But know that, outside of this, here you still have your self-connection, which is not affected, right? So then, yeah, each neighbor of a given relation have this normalizing factor, which is normalized by the node degree of the relation. And then you also have your self-loop, and now you would still aggregate with the sum and sigmoid like before. So yeah, so that's a more straightforward and a standard way of handling heterogeneity. Now I will spend the rest of this part on discussing temporality in RDL, and then what are some ideas we can take from temporal GNNs to bring into relational deep learning. So I'll break this down into 4 different sections. So start with time granularity here, and then we'll talk about different time encodings, what are the effects, why they are different, and then different temporal neighbor sampling strategies. And then for the last part, I will talk about kind of the core concept of temporal graph learning. So how is this different than the standard GNN training, right? Which is what I call the chronological training. So the real-world data and task, as we see before, are often temporal. So the edges have timestamps, and new users will emerge. So you cannot assume anything will be constant. So you cannot assume that you will have the same set of users. You cannot assume that the number of edges in the graph will be fixed, for example, right? And then the task itself is also temporal, which means that the output of the model is also different depending on time, or it should be different, right? So the goal of temporal learning here is to learn the temporal and structural patterns from your database, and then apply that to predict future tasks, right? And as Harald mentioned before, time is first-class citizen. So basically, you want to use what you have observed until now. So in a tabular setting, think about that's everything you store in your database until today. And then as time goes on, there'll be more things being registered into your database. But what you have right now is the information until today. And then how do we leverage this information to forecast what will happen in the future, right? And then the key thing here is you also want to avoid any temporal leakage. Okay, so I will talk about the first topic, time granularity. So what do I mean by that? So the concept of time granularity is, well, quite straightforward. It's more like you have seconds, you have minutes, you have hours, and we have days. And we work with this concept every single day to organize our schedule, right? But then what does this look like from a graph and a data point of view? So this is what this figure shows, right? So when you have like the 5-minute signals at the bottom, which is the most fine grain, and you can see a lot of finite details, right? It's also kind of noisy, right? There's a lot of changes, and then you smooth it out to 15-minute intervals, and then go to 60 minutes. And then I guess the most drastic is the 24-hour interval. You can see that all the finite small details that you have at the 5-minute interval has been removed. Now it's just the big picture because now you are getting one data point per 24 hours. So the coarser the time, the more smoothed out the signal is. So it gives you more high-level view, but it loses more on the local dynamics that you have in the data, right? And then here is more a graph visualization. So, so when you are thinking about your relational graph, you need to pick the correct time granularity, and this is very important. So, so how do you do that? So let's say you have a underlying time granularity of your data. So let's say your data come in every single second, but then you still want to look at your data in different ways, maybe at a different level of time granularity, right? So this is called discretization. So basically, you can beam a bunch of time points into fixed size time intervals, like minutes, hours, and days. And then, as I mentioned before, the more fine grain you have more information, the more coarse grain you have less information, and you lose information. And then what happens on the graph scale, right? So when you have the 5-minute graph, so there are small clusters, of course, but many things are disconnected. And there could be many single edges. And then you go to 1-hour graph. Now you see the emergence of large connected components. And then now you go back to 24-hour graph, right? In that case, it's basically fully connected, right? So you lose a lot of the fine-grained community information, the interactions. So that's why it's always very important to understand your task and then what time granularity it requires and what is a good one to select for your model, right? And then here are some just numbers, benchmark numbers from a recent paper of mine. So basically here, I'm not going to go into the detail, but basically there's a way to train GCN to perform temporal graph task in a straightforward way by basically projecting it to finer grain time granularity. But the TLDR is that you can train GCN on different level of graph snapshots. So the table here shows that when you train GCN on hourly snapshot, it get about 51%. Then if you train on daily, it can go to 70%. And then you go to weekly, then it goes to like 39%. And we see this not just on GCN, but also on a different temporal graph model. So we see that there is this pseudo-optimum for each of the model where it has a large amount of information within this time granularity, and that's most suitable for the task. But there's not too much information such that it draws out the finite details that you need to complete the task. So yeah, so again, going back to my point about choosing the time granularity, right? And then in a temporal graph, there's two different representations, and then these are basically two sides of the same coin. So the discrete time ones are more looking at snapshots, more coarse grain, and then the continuous time ones are more fine grain. These are second-wise interactions. Okay, and then so moving on, then we also want to learn how to encode the timestamps, and then we also want to see how do we retrieve past interactions and then use that information for prediction. So so I will get to those one by one. So let's look at some time encodings. So so the main takeaway here is that you just need to know two things. There's two main categories of time encodings. One is absolute time encoding. One is relative time encoding. So the Unix epoch time is an absolute time encoding. It is grounded in absolute real-world time, right? So here, this only move forward in time. This absolute time encoding will never repeat because the real-world time doesn't repeat. So things will happen sometime in the future, but no two things like for one given timestamp, there's no repeating it, right? So this makes it hard to compare timestamp. So you need to do a subtraction operation. While the relative time allow us to perceive events um, in relation to the time of interest. So this is what's mainly used in the ML part for temporal graph models as well as for RDL. So so here you would look at the difference between two timestamps, say T1 and T2, and then you basically compute this delta T, right? So the relative time allows you to basically start from zero. So it's kind of a normalization. And this is very easy for you to capture recency bias. But because what you will do is you will look at when is my time of interest, like today, and then compare that with a past timestamp, and then you can compute the relative time difference. And in terms of how to do time encoding, like one of the most widely used is this learnable embedding of time, of the relative time specifically. So here, the goal is to construct a temporal kernel that basically can Hello? Okay, I'm back. So yeah, so for this one, you can model directly the delta T through the kernel, right? And then the key idea here is that your temporal kernel should be translation invariant. So this means that if you shift this by any constant, you still get the same delta T back. So that's very intuitive. So you want your model to behave in that way, right? And then, so the most commonly used one is this one based on sine and cosine frequencies. And you make the frequencies to be learnable, essentially, right? But of course, there are many different ways of modeling time as well. And then I will talk about the temporal neighbor sampling, which to me is very fascinating, but also we don't really know which one works best yet. There's all kinds of approaches out there. And I will just give you some ideas about what people have tried, right? So when you do temporal neighbor sampling, there's two things you want to think about. One is who is spatially adjacent to me. So starting from a node point of view, right? So that's the graph connectivity. But then you also have the temporal connectivity. So who are more adjacent to me in terms of the time that I'm doing the sampling, right? And this changes, right? This changes all the time because if you move time forward, then your set of neighbors changes. Their interactions might be different as well, and so forth, so on and so forth. So the most simple one, this is from a recent work, I believe that was also presented at the poster session. So they proposed the time context sampler, where the idea is that you simply sample purely based on time proximity, disregarding the graph structure at all. And this can actually get you good empirical performance. So yeah, so I find this to be very interesting. And then from a graph researcher point of view, this is also like very interesting to think about why this works. And yeah, and then you also have the graph-based sampling. So here you take a more dominant role from the graph point of view. So basically, for each of the node, you would start with something like a uniform sampling, which you want to keep track of all the past neighbors or edges, right? But the problem here is that, well, the history might run very long, right? So then there might be many different neighbors that you need to keep track of. So this is not very efficient. So then you will need to apply some downsample strategy like uniform or weighted sampling, but that's still slow and not scalable. So what people do in practice is to use caches. So this uses the idea that you're always moving forward in time. So basically, as you process the data, you construct caches of things that you have seen for each node, right? So basically, after you make the prediction for the edge BA and CA, then you put them into the cache, and you see that I have observed them. So in the future, when you need to query who are the neighbors of A, you already have B and C in the cache. So you don't need to do this on the fly, but you just query the cache, which is very fast, right? So this is what we call recency neighbor sampling, which is you would maintain a cache of fixed size for each node, and then you update the cache when new edges arrive. So this is kind of like a first in, first out principle, and you push out older neighbors because you assume that more recent interactions is more important to you, right? Um, but of course there are problem with this as well, right? So you need to maintain the caches, and the caches are all fixed size. So in graph you have nodes that are more connected, nodes that are less connected, and they all have the same size of the cache, right? So yeah, so you have these constraints as well. And the last one, it's more kind of nice in the mathematical sense, is that you can also try some ideas like doing a temporal random walk. So here you will do your standard random walk where you have a termination probability, right? The alpha that you keep going or stop going. And then you also have an exponential decay over time. And this actually corresponds to temporal personalized page rank, and you can find more in the paper here. But the main idea is that you have a random walk with a termination probability. Okay. Okay. So the idea is that so you have the so you have the alpha random walk where the alpha denotes the termination probability. So that tells you if you should stop the walk at this hop, right? And then this is basically exploring the past neighborhood, similar to classical random walk. But then you also have the beta exponential decay. So this is used to explicitly model the recency bias in temporal graph. So the bias says that the more recent event to me are more important for my prediction. So then you apply this exponential decay to your random walk as well. And then this decay will ensure that you are only going to keep track of the set of neighbors that are most closest to you in the timestamp, or approximately sample it more based on the closeness in time, right? And these are just 4 different ways of doing sampling. And there's basically still many more ways that you can try to do sampling in temporal graph as well. And for the last part, this is more conceptual. So I want to talk about chronological training. So basically, how do you train a model such that it can leverage its information observed, and also the model can update itself perhaps during inference time as well, to leverage the new information coming in, right? So the key idea is that you always want to use information up until now to predict for the future. So then you need to train the model to utilize these newly arrived information, right? So there are 2 ways to go about this. So the one setting is you can do this live update, which is that you always are fine-tuning the model based on newly arrived data. Theoretically, this will give you the strongest possible performance, but also that you can imagine that this will be very expensive to do in practice. And in some settings, this might not be possible, right? And then the other approach is that you will train your model in a way such that it will always update its or adapt its embedding. So for example, like you can train a GCN to always predict for tomorrow's snapshot. So it doesn't matter um, like how big your data set is. The model is constrained to the information until current time t, and then always predicting for t plus 1. And you will train it over many, many days. So through this training, the model can learn to leverage that information. And also when it sees a new day coming in, it will use that information to do the prediction, right? And lastly, to put everything together, so we have a temporal graph attention layer. So I won't get into too much detail here, but as we are familiar with graph attention layer, we know that we want to dynamically pull over neighbors. Now let's just add this time dimension here. So, so the query key and value are all dependent on time now. And the goal is you are generating this time-dependent node embedding, which means that your node embedding and the way that you pull over your neighbors, the weights you assign to pull over your neighbors are all changing over time. So this now becomes quite complex as well. And the model have a lot of degree of freedom to kind of change the distribution of the importance that it assigns to the neighbors and shift that over time as well. So in this temporal graph attention or TGAT work, the idea is to use the TGAT layer that I just talked about, and then it would use a temporal neighbor sampling, sample a K-hop neighborhood, like the recency neighborhood, and then you will have the time encoding that we see from before with the relative time, and then we'll leverage the chronological training that I discussed. Yeah, and that's your recipe to build a temporal aware model. And I just want to point out some resources. So recently we have released a new machine learning library called TGM. So this is built from scratch for temporal graph data and temporal graph reasoning. So this is so this supports many of the state-of-the-art temporal graph models, and it also unifies both discrete time and continuous time graphs. So both of them are just different iteration of data in the library. So yeah, so please take a look if you want to try out some models. And then we also have a weekly reading group on temporal graph. And then we will usually discuss some newer papers, and including many of the paper from RDL as well. Yeah, and so now take some questions.
Okay, so I just have a quick question. So what's the connection with the relational deep learning that we just talked about? I might be a bit lost in the big picture.
Okay, so do you want the quick answer or the short answer? Sorry, the quick answer or the long answer?
Might be a long answer.
Okay.
That could be possible.
Okay, so I will still give you the quick answer for free anyways, because it's quick. So the quick answer is that, the relational entity graph that is built from the tabular database is actually a temporal heterogeneous graph. And all the tasks that we do in RDL is a temporal task. So you are trying to predict the future, right? And the long answer is that basically many of the concepts that I have discussed are actually implemented in the state-of-the-art RDL architectures that BJ will talk about as well.
Okay, so I think I have a few more follow-up questions regarding
go
your
ahead.
answer. So first, do you think it is necessary to strictly use these temporal graph learning paradigm in training relational deep learning models? Because if you just want to predict some missing values, then I would imagine some future values would also be useful for some earlier to predict some earlier values, right? So you don't necessarily have to follow a temporal or chronological order in your training.
Yes, so I think so in temporal graph learning, there's also tasks that are doing kind of like injection, so kind of filling out missing information. So you can do that as well. So it's not necessarily a clean take, um, but but yeah, if you want to just complete the table, you have some missing value, then you can probably just do some standard ML like
Yeah.
missing information completion.
Yeah, so that's my question. So why is it so necessary to strictly follow a temporal order when you train instead of just, doing some mask training?
Because for your real world task, you want to train the model to, so for the real world task that many of the company care about, it is about predicting what the user will buy or purchase or interact or unsubscribe, right? So these are all future prediction tasks, and you don't do it just once. You do it multiple times, right? So you should have a model that are trained and are able to leverage all the possible information to do that. And yes, you can also understand it as a table completion problem, but that's usually more from a single table point of view, right?
Okay, I see. So I guess the short answer would be in real world tasks, like a lot of them is strongly associated with time, and we kind of want to predict future. Did I understand like that?
Yes, essentially.
And I guess um, if there's still time, I want to ask another question. So how do you, so the timestamp here is actually associated with nodes if you actually want to understand it in the context of relational deep learning, right? Because each row in the table has a timestamp, I would imagine. But your edge actually connects two rows in two different tables by primary foreign key association.
So,
right?
so when you have a transaction table, so let's just do a basic example. You have user, let's say you, and we have I don't know, Starbucks coffee as an item table, right? And then you purchase coffee. You purchase coffee. Your transaction is its own row in a separate table. So that's where this is kind of like an edge in a sense as well. It has a timestamp to it. So it depends on the nature of your table as well. So the tables can represent not just nodes, but could be some sort of complex like interaction between multiple tables as well.
I mean, could you just add a row in one table that has a primary key that refers to a foreign key uh, in a row, in an earlier row of another table? Like in that sense, like you have two different timestamps. One timestamp is the row of the primary, uh, that has the primary key, and the other row is the row that has a foreign key, but that row happens at a very early time. Then you basically have two different times. Would that be possible? Is that a possible scenario? And how, in that case, how do you define the timestamp of that edge?
So
So for this question, I think we don't have defined like timestamps for edges because let's consider an example where you have an edge between two rows, table one and table two, and there's a timestamp for the row one in table two and then the row in table one as well. So the edge timestamp can actually be formulated as a function of the individual row timestamps. So I think that's the answer to the question that the edges don't have timestamps, although we can actually make a composite formulation that allows for that.
I see. That answers the question, but I guess one comment would be that would be a little bit different from a lot of temporal graph learning setting where the edges are timestamped themselves, right?
yeah, so I'll answer this one. So I think in terms of how you formulate so the TLDR is that in terms of how you formulate it precisely as a standard temporal graph learning task, that is still an open question. That's not being done yet. So, but I think there's many things that we are doing in RDL that's already temporal graph adjacent, which is like the recency sampling or the temporal neighbor sampling, and then the time encoding is pretty much very similar as well. So there are many similarities, but in terms of how to bring the entire modeling of temporal graph we have done into the RDL space, that is still like, like a research question. Yeah. Any other questions?
Thank you for sharing. You mentioned the importance of granularity when we apply this temporal network to specific problems. Is there any general guideline for us to choose granularity, or is almost completely problem specific?
So, okay, so I can answer this in two ways. So there is a guideline that I follow, and also there's no general guideline. So the guideline that I do follow is that if your model is something like GCN and so on, you should pick a time granularity such that tomorrow is not empty. So for example, you have a stream of interactions, right? But then you want to pick, the way to bin it, right? Basically the time intervals. So you want to make sure that at least there's something in each time interval, because you don't want to deal with like empty graph. Like you don't want your model to be saying that for today I'm predicting for tomorrow, but then for the next one that'll be like 1 week down. So you want to make the time granularity such that there are graphs every single day, for example, right? So that's basically the heuristic that I follow. But in terms of general rule, I think that's a very interesting research question. That's something that we just added to TGM as well. So now you can just pick the time granularity, but it's still like there's no one answer to answer that. And I think it would be nicer, like a nice theoretical paper, if it's possible to show some connection there.
Thank you.
And yeah, so now I'll hand the mic to Vijay, who will talk to us about the next section on frontier architectures.
Just a quick announcement. If you need Wi-Fi, there should be a Wi-Fi called ASU Guest. So this will be important for when you want to follow along in the hands-on activities.
Yeah. Hello, everyone. So thanks, Harilaus and Andy. So far, we've been able to cover like what is the motivation for relational deep learning, how does relational databases, like how are tasks defined in relational databases and how they can be framed as proper graph neural network or graph learning problems. What are some of the background in graph machine learning with different kinds of neural network designs and unique challenges of heterogeneity, temporality, etc. So now I'll come to the next section where I'll cover some of the frontier architectures for relational deep learning. There are broadly five. The first, I'll show how a graph neural network can be used as an RDL model. I'll show some results there compared to traditional machine learning methods on relational databases, which is a very old topic because prediction tasks have been of interest by the use of models such as XGBoost, LightGBM, Random Forest. So I'll show some comparison with that in the first section. Then I'll show how some explicit structural mechanisms which some of us were discussing in the questions, for example, many-to-many relationships across different tables, how they can be modeled explicitly. So that gives rise to the RelGNN architecture. Then we'll have an LLM that can be used for prediction tasks in RelBench or any RDL, which is the Rel LLM. And I'll conclude with graph transformers and graph perceivers, which are like the recent graph transformer based architectures for relational deep learning. And some of these are also used as um, uh, representation backbones for relational foundations and models recently. So let me start with the overview so far. Like we see in the graph machine learning side, like we can apply most of the networks that have been developed for general graph learning problems in relational deep learning. And we have the relational tables along with the training table, which has the entities, the task labels, and the time. Uh, these results in relational entity graph. And if we convert that to a computational graph similar to what has been used in graph neural network, on the right here, we can see that for learning representation of nodes A and B, we can traverse across its computational graph and apply a GNN similar to how it has been used in in a variety of other problems in the last like 5 to 7 years or so. So the main role of graph neural network in a RDL setting is that it allows for a representation learning on the entity graph, and that representation learning power is kind of automatically executed by the node's neighborhood. For example, if I want to learn representation of the the user's computational graph is consisting of the links that it is represented in the original relational tables. Users are connected to transaction and transactions are linked to products. So a GNN computational graph against that user will be used to obtain the node representations that which can be used for prediction tasks. And compared to feature engineering, this is kind of enabling an end-to-end automatic feature representation learning step instead of spending time to design hand engineering features, which was most of the cases like in traditional machine learning on databases, which Harilas also provided a very detailed background on earlier. So the advantages of GNNs is that GNNs can give a better representation learning pipeline instead of handcrafted features, and in essence it is the learnable version of feature engineering or maybe the feature building of entities against which we want to do prediction tasks. um, GNNs can learn to aggregate information. For example, if let's say we were to define certain SQL rules for building feature representation in traditional data scientist kind of workflow, we would have to think hard on what kind of rows to discard, what kind of rows to include. But GNNs can learn to aggregate information automatically and discard things which is not related through the model training, and that happens end to end. And thus they can detect fine-grained information. For example, if certain behaviors within the last year, uh, something which is informed by the temporal information or timestamps, if they are important, the graph neural networks can automatically detect such patterns, and we don't have to rely on explicitly cutting this out, because for thousands of tasks there can be thousands of patterns which would reflect fine-grained like information that we want to model or not. So the GNN is used as an RDL model. An end-to-end pipeline looks very simple, similar to how any other end-to-end graph learning or graph ML pipeline would look like. We have the input relational entity graph. We do a temporal aware subgraph sampling in order to create a computational graph that we can use for in the GNN. Why? Because the relational entity graph may have hundreds of millions of nodes. So we cannot actually process the GNN on the entire graph, but instead, whenever we have a prediction task against a seed node, we sample a subgraph against that seed node, and sampling can be done in a variety of ways. But one thing is important is whenever there are prediction tasks defined, as in the previous sessions, like you heard, like temporality is a first-class citizen. So we always make sure our subgraph sample does not contain nodes that leak information from the future. So this subgraph is something which takes the neighborhood context for timestamps up to what the task demands. And then we apply a graph neural network that can model the dependencies similar to how the dependencies of the graph that are the characteristics of relational entity graph, and we do the prediction. So we can apply this again by using standard machine learning workflows, and we can use PyTorch based libraries like GNNs that is available in PyG, and PyTorch frame is something that is used to convert the relational databases into vector information like multimodal node information. So towards the later of this tutorial, we have a hands-on demonstration that kind of implements this GNN as an RDL model, and we will show the complete pipeline that is present in this slide in a collab notebook towards the end of this tutorial. So stay tuned. But I'll come for the results now. Like when a graph neural network model is used as an RDL model, how does it compare to traditional methods? So compared to, we showed some results on RHEL-Bench, all the different kinds of tasks on RHEL-Bench. If we compare RDL, which is simply a GNN, in this case, it's a graph stage model that's deployed on, that's trained on different tasks. In this case, the entity classification tasks. We see that there's a very consistent performance improvement, except for like the RHEL trial study outcome where there are some minor performance drops. But except for that, there's a consistent performance improvement compared to the gradient boosting machines, which is on the left part of like RDL in this column. And the gains are up to like 30–40%, in some cases even 40%. Like we can see if the task is to predict the user engagement in the RHEL Stack Overflow database, we can get up to 90% prediction of the correct prediction of the tasks compared to 65–63% of the predictions by using traditional models. So this is showing the advantage of using GNN as an RDL prediction task model. On entity regression, also we see a comparatively performance improvement as compared with light GBM, except for like 2 or 3 cases. We see a consistent performance improvement. But having said that, regression is a very challenging scenario. I would like to join like Harilas's point earlier that LMs struggle in regression. They definitely do compared to GNNs, but even for GNNs also regression is a very challenging task, and like the problems here are very complicated in the sense that we have tasks such as user LTV. So this task is to predict the user's long-term value in an e-commerce platform. We have driver position, so it relates to driver's position, regressing that value in a Formula One database, sales of items, etc. So these are very complicated tasks, and there's a big gap to fill, and I'm sure like this will be a topic of interest for many of us here in graph machine learning. But yeah, regression, there's a lot to improve, but the bottom line of this slide is that we still get slightly better performance, and in some cases significant better performance when we compare to traditional models such as light GBM in this case. And for link prediction also, which are recommendation tasks, trying to connect prediction information such as whether user will visit an ad, whether user will purchase certain items. So the mean average precision in these tasks as well kind of improves significantly, and perhaps some of the highest improvements that we in the recommendation results, which are like the link prediction tasks in RHEL-Bench. So across the board, we see the use of GNN improve performance in RHEL-Bench. So having said that, like we still have a lot of avenues to improve, and there's an architecture that our team developed, which is RHEL-GNN, that tries to look more deeply into how the relational structure can be leveraged, and it answers yeah, it may connect to some of the discussion points earlier in regarding how many-to-many relationships can be. Yeah. So RelGNN is a improved GNN architecture that leverages the unique structure that is present in relational entity graphs, and this answers some of the questions on discussions we were having earlier regarding many-to-many relationships. So we observe that edges in relational entity graphs, they have some uniqueness in terms of like how every edge is by default a primary foreign key links. So when we look at customers and products, they're often connected through certain transactions. So if there are many-to-many relationships between customers and products, they they may not be directly connected because of the nature of how primary foreign key links works in databases. And because of this, they have to traverse, for example, if a product has to send information to a user, they have to traverse through the transaction nodes, and the many-to-many associations cannot be encoded by the single primary foreign key edges. So uh, these are some of the examples. Like races are connected to drivers through standings, and there can be some other hub-like structures. But these are just examples to show that there are many-to-many relationships in relational databases, but there are always some junction tables that connect them. And this may be because of the some of the standardizations of how databases are defined and constructed in terms of the schema, but it may prove certain challenges in terms of the information that we may want to model more efficiently. So because of this kind of junction tables and like certain additional tables which models many-to-many relationships, there are a couple of limitations that can be observed. First is the junction nodes are what the one-hop neighbors become, and the most informative nodes, or the tables that supply the most important information, are actually two-hop nodes. And we can see this in this example, like the product that the customer purchases is associated with the two-hop node information. And we know, I mean, all of us being in this field of graph machine learning, we know like as we go from first neighbor to second neighbor and so on in the computational tree of how a GNN works, there's a neighborhood explosion. Like as soon as we go from hops to we increase the number of hops, the information that we want to incorporate becomes very challenging in terms of the scale. So we may want to focus on this. And the second thing is the redundancy. Like if let's say I want to apply a GNN at the transaction node in the second hop. So some of the information from the source node may be passed to the junction node, which is not kind of important, and it may create a redundancy in that case. So in order to resolve that, we observe that we can define these kind of many-to-many connections as atomic routes, and they can be derived automatically without having any manual intervention. If some of you would have worked in heterogeneous information networks or heterogeneous graph learning, you would have seen like some terms such as metapaths appearing very often. And metapaths require some manual intervention to kind of draw some atomic information elements. It could be like paper authors and citations, some composite relationships across that line. But these kind of atomic rates can be defined by just looking at certain hop structures and bridge structures without relying on domain expert knowledge. And the change is that we define message passing based the message passing is kind of modified to reflect this kind of atomic routes. So now we have an example where we can allow the information from transaction and products to be passed in one step to the customer. And the equations mathematically, it's just showing there's a fusion step that enables it. Nothing very fancy, but it is very influential in trying to improve the performance even further of the GNN. So the story here is that we saw GNN as very naively extending on RDL. It improves traditional data science workflows. Now, with further enhancing the GNNs, we improve even further, in some cases up to 25% on the prediction tasks. So yeah, so far we covered like two of the architectures. Let's move towards answering some of the questions which Harilaos like kind of poked in a between, like why not use an LLMs. So there was a very like the whole slide, there was a prompt like if we textify information from relational databases, it may look like an ugly prompt that is fed to text of an LLM. So we try to look at this question, like how to repurpose LLMs for these relational prediction tasks. So the first thing is like we could textify, and then this is what a textification would look like. The exact dense version of this was included earlier, but here we can just we're trying to predict certain things on the customer transactions and products, our input texified information would look something like this, and people have done this. So relational structure data can be converted to text prompts, but the challenges are we are explicitly losing the structure information that can connect, for instance, certain products with certain users at certain timestamps. So we're kind of flattening everything, and we are losing the explicit information about the graph structure. It also leads to certain redundancy in the prompt constructions. For example, we can see that the 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 token on timestamp is repeated as as many rows it sees. The if the rows has timestamp, the attribute timestamp corresponds to certain tokens in LLMs. It keeps on getting repeated, and in actual real world cases, when we have a prompt that can represent certain 300, for example, 300 nodes, there'll be a lot of repetitions of certain words. So there's a massive redundancy in these prompts, and as a result, we also lead to excessive long inputs. Like if I have to represent a 300 node or 300 rows from a database, it would just be like 300 times D information at the starting of a graph neural network. But if I want to textify that, and some of the attributes in databases may have text, it will lead to excessive long inputs. So these are some of the like inherent challenges in using LLMs for RDL of the like on the fly. But we can actually convert uh, like the graph structure information to an embedded context that can be used as a soft embedding or soft prompt for an LLM. And we because we have established the connection of relational databases with graph machine learning, we can use a graph encoder that converts relational data into embeddings, and these embeddings can be used as soft prompts. So how we do is that we can apply all of the things that we have seen so far, like graph neural networks or relational GNN or any other network that can be RDL instantiation. We can use GNNs to generate node embeddings, uh, which can be fed into an LLM. And these node embeddings will follow a similar pattern in how the graph neural network was applied to an RDL, like a local subgraph. For example, if the question is whether a particular user will be engaging with certain ads, um, so for that user, a local subgraph can be sampled, which would look something like this, for example. And we feed that into a GNN, which can be, for example, feed this graph into a graph neural network, and then we get embedding against everything. So we kind of pack those embeddings, and we feed these embeddings into an LLM along with the task and data description. So this is similar, like we are trying to read or we're trying to chat with our database, and the format of this is simple in as compared to how other multimodal LLMs are used. For example, in VLMs, some primary versions, or maybe the ones that are kind of open source, also use image embeddings that serve as soft prompts for LLMs, which can be used as a natural language interface to chat with images. So this interface is primarily very similar, and we can use MLP heads for doing regression, or for classification. We can just let the LLM do some prediction. So the goal is the main idea is that we are using the relational deep learning pipeline to get embeddings that can be fed into a large language model, and as such, LLMs can be repurposed to do prediction tasks for RDL. So Yeah, and for some certain details, like there are elements here which can be trained, and we keep the LLMs actual core parameters of the LLMs frozen because we don't have additional text data to train here. Rather, we're trying to repurpose the model to learn predictive signals for different input subgraphs for seed nodes. And we can the training and fine tuning involves masking certain elements that we are getting from the input databases and making converting them as a prediction task. For example, if we have income columns, we mask them and those becomes our labels. For fine tuning, we can use the same labels that we had for RelBench or the relational deep learning prediction labels to do fine tuning, and it can answer questions such as like whether the customer will perform any review in the platform in the next 3 months, or what is the amount of uh, uh, products that a customer will buy in total. So these are certain downstream tasks. So the key idea of this is to like, yeah, how do we adapt the LMs for prediction tasks, and we do this by simple like training and fine tuning that involves large language models parameters as well. So if we compare this with in context learning, which is basically if we would just textify the prompt and feed in that context, that is the green bars. The orange bars is what we get with REL LLM, and these are certain prediction tasks in REL bench. So we see that there's a consistent performance improvement that we get. But what is more important is that we see a massive reduction in the error bars. Why? Because when we design prompts, there's a lot of variation in what the prompt should be in order to convey the information that is oh, okay. Yeah. So the comparison to the green versus orange, like one of the key observation is that when we just textify the relational structure data and convert them into an in-context learning task, we see there's a big variation in the performance, and this is contingent on the fact that the prompt design itself is challenging, and we may have to do a lot of arbitrary decision making in what are the number of tokens that we are trying to select for different entities. What is the size? Where are we cutting? What is the number of neighbors to select? So these are there are some of the arbitrary designs choices here, because of which the prompt may not be very informative at every run, and there's an error bar corresponding to this. And overall, we see performance improvement of LLMs compared to ICL. Compared to the RDL, simply using an RDL, we don't see massive performance improvement, but that was not the initial goal. Like the goal of this was to show that how LLMs can be used for RDL, but not to like show that this is kind of completely producing a new predictive model for which like the GNN or RDL model is itself very like very very good, or maybe like high performing already. And these are some additional performance comparison. I will not go much into detail here. But yeah, one of the limitation is that the graph encoder here is not a general graph foundation model, which also motivates the need that if I want to repurpose any LLM to any relational deep learning task, and I compare this to how vision language models are used, I would need this motivates the need of a general graph foundation model that can use an encoder. So if let's say this was an image, we would have a vision encoder that would give me vision embeddings, and I would not have to train that vision encoder again and again for hundreds of tasks. But in this case, I would have to train, like at least for the context of this work. If we would have some general graph foundation model, we can actually turn any LLM to a natural language interface to talk with relational databases and perform prediction tasks. So this is just to motivate the development of graph foundation models. Uh, Next, the graph encoder used for the context of this work was GNN based. While we have seen like graph transformers have been like they have excelled at several graph learning problems. So with this, I come to like how we can generalize graph transformers for relational databases. Um, like we've seen, like transformers can be seen as a from a graph perspective, that attention mechanism is a special case of message passing. If we have the transformer on the left, it's similar to having a node, and the information being message passed from the nodes that it's connected with. And the second key observation, if we look transformers to the graph lens, is that positional encodings are functions of the input data structure. So the original sentence transformer or the transformer that's applied on sequences, they have an implicit line graph. If we try to apply a graph positional encoding functions on this line graph, we can reconstruct the original positional encodings that was used in transformers. So this is just to give a kind of recap on the graph perspective of the original transformer. And it has been used to develop graph transformers from a variety of different designs, but broadly three key ingredients I would like to make, like in terms of how to design a graph transformers. It has attention mechanism, that's the information exchange function. It has positional and structure encoding, that's a way to encode information about every node's graph context. This is to kind of show what is the positioning of each node in my original input graph, and there are different examples of positional encodings. And the third is like when the attention is executed, it must have abilities to handle different to different degrees local features as well as global features, which are shown to be helpful in different task-based scenarios. But roughly these are like, this is like a recipe to construct a graph transformer, and there are different instantiations. But the observation is that, and I'll start this observation with the main like the original text transformers. Like in the original text transformers, the input token is represented with two elements. The first is the token ID, which is the feature of a token, and the second is the position ID, or some positional element, which is the structure of that token in the original data. Graph transformers primarily keep the same formulation. An input token is represented with two elements, where we have the feature and structure. But with this, there's an issue. Like most graph transformers so far have been designed for static and homogeneous graphs, which we're not dealing with today. Like relational deep learning presents a new frontier or new challenge in the whole of graph learning, where we are kind of grouping everything under one unified lens. Like we don't want temporality to be treated differently. We don't want scale to be treated differently, but everything presents together. Like we have the ultimate ultimate testbed to make progress in different fields. But so far, graph transformers were designed only for homogeneous static graphs. So if, let's say, I had to relax this in the same way, I would have to define graph positional encodings for the homogeneous structure, the heterogeneous structure, the temporal structure, and each of them are costly to compute. So, and if, let's say, I was to show some maybe experimental observations, if I take an existing baseline, for example, heterogeneous graph transformer, and do a positional encoding computation, we see an additional time for positional encodings at every epoch, and this is a runtime per epoch. So we figure out that this is not scalable because now we don't have a single adjacency matrix that represents the homogeneous graph structure of relational database, but rather we have different elements of A, which corresponds to their heterogeneity, their actual graph structure, temporal structure. So we try to simplify how we want to represent our tokens. So we do this in the resulting architecture is called relational graph transform. But the key part is that we improve this design so that we can get the information from the graph structure more cheaply. We don't have to perform any complicated operations that takes time or involves redundant like computation over the graph structures. But yeah, this is what we do. We use multiple elements instead of just the two elements to represent the graph structure. And we do this by converting the relational entity graph to a sort of tokenization that is similar to sentences. For example, if I have B training nodes, I would have K nodes against each of them that would be sampled from the local subgraph. And for each of these nodes, like every dot you are seeing here, I would represent like with 5 tuples, like node features, the node types of the nodes, the hop distance, which is the relative distance from the seed node, the time, which encodes the temporal component, and one vector that is like encoding the subgraph around a graph. So what happens is, let's say I have 3 user nodes for which I'm trying to predict a user action or some similar tasks. So there are these are local neighborhoods that I obtain for each of the nodes. So I'll just show for one nodes. Like this is my user node, and these are like, this could be transactions, and this could be like products. What I do is, for each of these nodes, I have like 5 elements. And if you look carefully, these 5 elements kind of inform most of the things, or maybe all of the things that we need about our input data. We have the node features, the node type, which is the heterogeneity, the hop distance, which is the homogeneous graph structure, the time, which is the temporal graph structure, and the subgraph, which is a learnable component showing certain homogeneous structural relationships across these different users, items, transactions, or whatever the tokens I have. And I would apply element-wise encoders to each of these according to the input data type. For example, for the node feature, I would use a multi-model encoder, which is based on torch frame. For the others, if it's an integer, I could simply apply an embedding. If it's a floating point, I could apply a time encoder. And for the subgraph, which is a subgraph representation of like how this local neighborhood is connected, I would simply apply a lightweight GNN encoder, which would construct a vector against everything. So we get 5 different vectors, and we can add them to obtain the initial token representations, and we can apply a plain graph transformer over top of this. So the key in relational graph transformer is kind of uh, handling how we're modeling the input information elements that forms the tokens, which can be fed into transformers. And for the transformers also, we have an additional component that can model global information. And the global information is something that's not mandatory, but there are tasks in which they can be useful. So we do have an element for that. And this global information is kind of a learnable centroid. You can find more details in the paper, but the key idea of the global centroids is that if I'm feeding at every training step only a partial subgraph of nodes, there will be certain information apart from that subgraph which may be useful. So the global centroids is a way to keep those rough information, and when it's needed, uh, we have access to that. So so this is the overall flow. We have the entity graph. We change the subsampling and token preparation stage, and we apply a transformer, and we do prediction. So we just replace the subgraph sampler and the GNN with a new sampler and a transformer instead of GNN, and we have the relational graph transformer, uh, which performs competitive and improves over GNNs. And because transformers are general, they also can be leveraged. They can be used to leverage all of the advances that we have seen systems-wise or computationally, and it has been used like for foundation models, for which Harilas will talk. But I wanted to conclude this section with a small enhancement that has been seen recently by a work called Relational Graph Perceiver, which is a work from SAP. And I can remember that there was a poster of the same paper here. So if you want to check out, you can see. But there are 2 key enhancements that is seen in the relational graph perceiver work. First is the use of perceiver architecture inspired cross attention models, and the second is there's a separate temporal sampling. And this is interesting because I think Andy had a question earlier, like how is temporal graph learning helpful? So you'll see this in this work is that if you are having a capability of separately modeling pure time context instead of time-aware graph context. And I can clarify this term if it's too complicated. But what is done is, like, when we have neighborhood context, which is what we do in the GNN in the relational graph transformer, if we complement this with a purely temporal context, we see a performance enhancement up to 2% compared to just relational graph transformer. And how it's done is, like, for each of the seed node, for example, if this is my user, the neighborhood context would just inform that it's connected with this cell transaction and this item transaction at this time step of the query. But it's missing these two nodes that happened in the recent timestamp and these items that were bought, or maybe these another cell transaction that was executed in the timestamp. So the temporal context prepares like all those nodes without looking at the neighborhood structure and has a different representation that incorporates this information. So we have two kinds of sampling going on here. One is temporal aware neighbor sampling, which is the default that we have been talking since the start of this tutorial. But in relational graph perceiver, we have an added term, which is the temporal sampling. It just looks at the recent and kind of encodes a pure recency bias, and these are the like performance enhancement. So we can still like play with these kind of small but very useful and very impactful like gains in our models across GNNs, across graph transformers. And now I'll hand over to Harry Laos, who will see how some of these models are used in foundation models, but also like some of the new exciting works that we have been doing at this frontier, and how we don't need to have different models for different tasks, but instead can apply certain techniques to convert like to build one model that can work across different RDL tasks. So yeah, we can take questions maybe. Yeah, if yeah, okay. So I can take maybe one question, and then towards the end we'll have more time for discussion more comprehensively.
Thanks. Just quickly on the element-wise quintuplet that you're putting into the rough or to the transformer.
Yeah.
The subgraph. Can you give an example of what that is?
Yeah, sure. So let's say this is a user, and I have like k nodes that I've achieved from a subgraph sampling. So in this token representations, I don't have any kind of structure. This is just a flattened set of tokens, but they had a structure, and they had this structure. For example, this user did 3 transactions, 2 transactions was linked to products, and there are also some purple, like these purple nodes are kind of more into detail. Like if let's say there were only less than k tokens, these are some filler tokens. So this represents a subgraph that that helped construct, or maybe that was used to sample these tokens. So the fifth element, which is a lightweight GNN encoder, will just inform vectors against each of these that reflects the subgraph against with which it was sampled, like this local neighborhoods was sampled.
Okay, so it's like the node perspective of that subgraph.
Exactly.
Yeah.
It's like a tree kind of graph structure. Yeah. Yeah. Thank you. And yeah, we okay. So we have one more question. But after this, I think we can take some questions towards the end.
Thank you, Vijay. Very good presentation. I have a question. For the ICL scenarios for few shot or zero shot,
Yeah.
You have two architecture, RHEL LLM and RHEL GT. Do you have any preference based on your experience, which of them can be a better fit for these scenarios? Other than the size, for example, the LLMs are much larger than the graph transformer base, maybe 5 times, 10 times bigger. But other than that factor, do you think that any preference for RHEL LLM and RHEL GT? Just give me your ideas on that.
Yeah, so thanks for the question. So I think there are two perspectives that can maybe affect an answer to this. So one perspective, like, do I care about using a natural language interface? So let's say, do I want to like use a chat interface to ask questions? If yes, then we can use RHEL LLM kind of architecture where the graph encoder can be a basic GNN or can be a relational graph transformer or any other network that can build graph representations. So this is the first answer. If I'm more concerned about having a chat interface. The second question, if no, that doesn't affect me, but rather I want to build a sort of a let's say an agent that can just do some predictions over an input relational database snapshot. In that case, I would say, we have even more improved models compared to RelGT or LLM, and Harilaos is precisely coming to that. But the key answer to this one is that we can enable better in context learning abilities by not just feeding in flat text, but rather like we can feed like multiple input output pairs, similar to how like Kumo RFM or TAP PFN based architectures are doing, or we can have a contextualization where we feed in certain task information in a context, which leads to a better zero shot and few shot prediction. So for the second part, I think yeah, this will be more clear to the wider audience after Harilaos's presentation. Yeah, thank you. Thanks for the question.
Okay, great. Thanks a lot, Vijay and Andy, for the great presentation. Now, it's kind of late, so we're going to discuss about some super cool stuff, in my opinion. So we're going to discuss how we can do some serious steps towards foundation models for relational database, for forecasting on relational databases. As Vijay mentioned before, we discussed about all the previous architectures, graph neural networks, graph transformers, hybrid models that involve large language models and graph encoders. And what these architectures have in common, or most of them have in common, is that they're kind of limited to a single database and a single task. Meaning, okay, I have an e-commerce network and I'm interested in answering lifetime value. Then I'm going to collect training data. I'm going to train a single model to answer one particular task or to tackle one particular task. Then I look at a different database and I'm interested in tackling lifetime value or user churn. Then I need to somehow collect data again, train a different model and answer. And again, this different model will be tailored for that particular task. So the question here is, can we actually do better? Can we somehow revolutionize the field of forecasting over relational databases the same way that large language models and vision transformers have revolutionized the field of natural language processing and computer vision? And, the answer is, we believe that this is possible, and this is what I'm going to ask I'm going to explain some first steps towards this direction. And, the reason why I'm somehow interested in the ChatGPT moment of forecasting over relational databases is because the promise of having a relational foundation model is kind of significant. So it will give us the ability to answer predictive queries in a zero shot or in a few shot manner over any database and any type of task or any type of query. And more generally, the broader impact would be to democratize AI for structured data, where non-experts have access to some predictive tools, and experts have a very strong initialization or a very strong, first architecture, a pre-trained architecture for their models. So I'm talking about AI for relational database, but I couldn't even fix the page number here. So okay, cool. So the first model that appeared which somehow tackled this quest, was the Kumo Relational Foundation model, the Kumo RFM. So the Kumo RFM is using the relational graph transformer that Vijay introduced as the backbone, and on top of it, it has some in-context learning capabilities. It have an in-context learning module which allows for all these few-shot type of prediction. So I'm not going to go into the very details. Some of the details of the architectures are public. Somehow the training data is not public. So another effort was from Amazon Science. So the model is called Griffin. We're going to discuss and compare against this model in 10 minutes from now. And also there is this blog post by Michael which appeared I believe in July, yeah, in July, this July, where Michael Galkin discussed how Google is using Graph Foundation model to do some tasks, some relational tasks. So, long story short, there is a lot of effort toward building foundation models and moving away from, let's say, graph machine learning architectures tailored or designed or trained for a particular task to a, let's say, more broad architecture that is able to handle multiple tasks on different data, maybe jointly. Yeah, so towards this direction, what we did is we very recently released an architecture which is called relational transformer. So this is different from what Vijay said. So there is this one word missing, and this word is graph. So this model is called relational transformer. What Vijay talked 10 minutes ago was the relational graph transformer. So I know it's kind of funny, but yeah, these are two different architectures. And the key idea for the relational transformer is that it is a transformer agnostic to the schema, and the difference, maybe the main difference, is that now we tokenize at the cell level rather than at the node level. So in general, there are three core contributions of this architecture, which I'm going to explain. One is the cell level tokenization. The second is the task table integration, meaning that we somehow leverage the auto-regressive labels of a particular node or of the database into our modeling and into our architecture. And the third part is that we introduce somehow a relational attention mechanism, whose goal is to somehow capture the intertable and intratable dependencies in the relational database. So I'll go one by one to explain this innovation. So the first thing is to explain what is the input representation to this relational transformer. And to do that, I'm going back to my favorite example of an e-commerce network that has a table of users, a table of products, and a table of transactions connecting users to products. Now, in the previous models that we described, each row is a node, and each node is a token. And this is somehow one of the main reasons why these models are kind of schema specific, because now we need to have some neural operators that, or maybe some neural networks, some linear or multi-layer perceptrons, some linear models or multi-layer perceptrons that operate at the feature level. Meaning, I have now a database with a different feature dimension. I need a different model to train. So, this type of design choice leads to schema-specific architectures. Now, what we're going to do in this relational transformer is that we will consider each cell in each table in the database as a different token. So we go from a node-level tokenization to a cell-level tokenization. So in order to do that, we're going to represent each token by three different values. The first value would be actually the value of the cell. So if it is a numerical feature, this will be the value of this numerical feature, or if it's a categorical, the value of a categorical, or if it is text, we somehow encode the text using a language model embedding. So that's the first element of this representation. The second element is the description of the column. So I have this cell here, then there is a feature that I have the description of the feature, and I'm using a frozen LLM embedding to represent the column. And the third element would be a representation of the table or a description of the table. Here I have a transaction table. I extract an embedding, a frozen LLM embedding for the transactions, and this is my third element in the triple. Now, what is the benefit of this representation? It's that it somehow unifies relational databases of any schema into a consistent input space. And the second cool thing is that we can somehow leverage cell-to-cell dependencies, which in some cases can be important. So that's how we represent its token in this transformer. The second innovation, which is kind of important for us, is the fact that we somehow integrate the label or integrate the task into the schema, into our modeling. So let's say that we are interested in doing user churn. So we have this task table with 3 columns. One column is a foreign key or the entity label. The second column is the label, the value of the label. Remember 0 for active, 1 for inactive, and we also have a timestamp. So we are going to use that as part of our transformer, meaning that these are also cells in our, or tokens in our transformer architecture. So the information of this user churn table are tokens in the relational transformer. So what is the benefit of this, let's say, type of design choice? That we can cast now any node level task as mask token prediction. Why? Because we have the value here, predict the value. So this is easy to see. And the second and very important thing is the fact that by doing that, we somehow add auto-regressive labels for task tokens, meaning I have a token for a particular user. I have information about this particular user from the past, meaning maybe the user was active in January, inactive in February, active in March, and so on and so forth. We can leverage all this information during the prediction time. Now, something which is very important when it comes to designing such transformer is how do we sample context. So from my experience, context sampling can make a big difference in the performance of a foundation model or a pre-trained model, especially when it comes to such structured data. For example, we are currently exploring different context sampling strategies, and we see that this can affect a lot performance of node level tasks, link level tasks, and different, and in general, different tasks that have different somehow characteristics. So let me explain how we do the sampling. So we follow 4 basic rules here, but we are working on more sophisticated techniques. So the first rule is that we sample a seed node and we hide the value. So we have this cool guy over here. This is the value of a particular seed node, and we hide this value entirely. Now, in the second step, we're going to include tokens or cells in our context that belong to parent table. So here, this is a foreign key. The foreign key is equal to 1. This corresponds to a primary key in the user's table. Where if this is our seed node, we're going to include cells from the seed node with this hidden representation, plus cell from the parent node, which are the cells of this row, of this user row over here. So this is our second rule. Now the third rule is we're looking at the parent node, and we are sampling neighbors of the parent node. How are we sampling neighbors? Let's say we look at this transaction table. One user has neighbors in the transaction table. How? We see here foreign key is equal. So the transaction table has 2 foreign keys. One foreign key is equal to 1. That corresponds to the user table. The primary key here is equal to 1. So we can include the tokens or the cells of this particular row in our context. But this particular user, before that, but remember, we also said that we are always including parent tables, so foreign to primary keys. So, which means that since we sampled this row and this set of tokens in our context, we necessarily need to add the tokens or the row from the parent table, and the transaction table has 2 parent tables, one in products and one in users. So automatically we add this products row into our context. Yes, so now the third rule, if we look at the users table, remember what we're doing right now is we're subsampling child rows, and this user can have different records in the transaction table, or in other words, different neighbors in the transaction table. So we can, for example, sample this row over here, or that row over here, or any other row that has a foreign key in this column equal to 1. and this is the way, this is how we're doing the sampling. Now, finally, remember I said that we include in the database a task table, and this is very important for our architecture. And so if you can see, the users table can have, or users can have neighbors in the transaction table, but they can also have neighbors in the user chain table. And these neighbors are labels from previous timestamps. So this is exactly what happens here. So we have a user that has primary key 1. We look at the user churn task table, and we look at foreign keys that correspond to 1, and these are foreign keys that correspond to other labels of a particular user. Now, and we're going to include such cells and such rows into our context. Now, one very important thing that we need to keep in mind is we can only sample from previous timestamps through the whole process in order to avoid data leakage and build meaningful architectures. So this is how we do sampling. The final part of the architecture is the attention mechanism. So we have 4 different attention operations. The first one is column attention. So we have this confused guy over here, or this confused cell over here, and we attend this cell or this token with all the other tokens in the same column. The reason why we do that is because we want to have a sense of what the distribution of values is with respect to a particular feature. So that's the first type of attention. The second type is we're going to attend over cells or tokens in the same row. And this is what makes a big difference in the ability of our model to adapt to different databases. Now, the third type of attention is a neighborhood attention, very similar to message passing. So again, I attend over or I mask tokens which are in my neighborhood. And finally, we do attention over all tokens in the context. So these are the 4 key steps. Now, let me discuss a little bit about experiments. So here, what we did is we test 2 different types of tasks. One is binary classification, and the other task is binary regression. And the way that we pre-train this relational transformer is by leave one database out. So meaning, let's say I'm interested in predicting something over this rel trial database. What I will do is I will train over these databases. I will leave this database out, and then I will try to do zero-shot or few-shot predictions over a particular task on the medical database. And the same, let's say, rule apply for any other task that we are testing our models on. So overall, we test on the unseen schema. Now, the baselines that we use for comparison is Griffin. This is the other foundation model from Amazon Science that I discussed earlier. The second baseline is by somehow serializing the database and the prompt into text, and then using Gemma 3 to prompt an LLM. And the third baseline is the RDLGNN, is a graph neural network which has been trained on a particular database for a particular task. So we have 3 different levels or 3 different types of baselines that we compare against. Now, the way that we did pre-training, we used 12 layers, and our model has 22 million parameters in total. We trained using mask token prediction on these 7 databases of relevance. We trained for 50K steps in total on 8 A100 GPUs. We used a linear decoder both for regression and classification. And for regression, we trained with Huberloss. For classification, we trained with binary cross-entropy. And this is the first set of experiments. So you see here in the left table some binary classification results, and in the right table some regression results. So here the y-axis is the test AUC, and in this vertical axis you see the zero-shot performance. In the blue line, this is the relational transformer. In the green line is the Griffin Foundation model. And you can see here in the orange line, this is a graph neural network which is initialized randomly and trained for 32K fine-tuning steps. So here is zero shot, and here in the end of the of the x-axis, we have trained our models or fine-tuned our models for 32K steps. So what is interesting to see here is that zero shot is doing fairly well, and you can improve performance with a few fine-tuning steps. Performance which can be somehow acceptable if we compare our model with respect to the fully fine-tuned graph neural network. So that's the first set of experiments in classification. But what is even more interesting is the pictures that we see in regression. So again, here this line is zero shot. So the test that we have is TR squared. So the higher the better for regression. And as you can see, this is our model, the RT, pre-trained RT zero shot, achieves 30% R squared, whereas the graph neural network trained on a particular on the particular database and the particular task, after 32K training steps, cannot reach performance of our model, cannot reach the zero-shot performance of our model, which I believe is pretty interesting and pretty cool, and somehow shows the benefit of pre-training or pre-trained models for forecasting tasks. Also, something interesting to note is that we can see a steady gap between our model, the relational transformer, compared to the Griffin baseline. More results here. So maybe it's too late to bother about the details. Maybe we can focus on this last line here. So this is the mean AUC for classification tasks. So this is what our approach, or maybe our pre-trained model, the mean AUC that our model achieves if there is the database is completely left out from the pre-training part. And this is what happens if we include the database during pre-training, but not the particular task. So there is some slight improvement as expected. Now for regression, so the performance is even stronger. So the proposed relational transformer is the only architecture which is able to somehow achieve some meaningful results better than the naive baseline. So, overall, these are numbers. If I had to summarize and, have a take-home point for this part of the tutorial, is that this relational transformer has 1,000 fewer parameters compared to Gemma 3. So maybe that's something important to keep in mind when you need to compare the performance of a large language model compared to a transformer architecture tailored for relational databases and forecasting, that you can use 1,000 times fewer parameters with much better performance, so 13% better zero-shot AUC. Also, we need a much smaller context for the relational transformer, the tailored foundation model architecture. And that's, let's say, the comparison between a foundation model for relational databases compared to a foundation model for language, so a large language. Now, overall, what I introduced in this 15 minutes was, let's say, what I think a serious step towards a foundation model for relational databases, a model which can do zero-shot forecasting on databases and tasks that have not been seen during training. And there is some strong or some significant evidence that you can transfer knowledge and patterns from one database to another, and also you can leverage this autoregressive information during your forecasting phase. Now, of course, this is a first step. There are a lot more steps that need to be done in order to have a foundation model that can operate over any database and any task. So for now, the limitation of this approach is that it's not able to perform well for recommendation tasks. We are currently working on it, and hopefully we'll have some interesting results soon. The second limitation is that this transformer has been trained with limited data, only 7 databases or maybe 6 databases of relevance. So we are trying to do some progress in this direction, either using synthetic data or more databases. And there is also a lot of room for improvement in cell encoder, adding better cell encoders and better positional biases or graph biases in the model. And with that, I would like to conclude this first, more maybe the oral part of the tutorial. And I would like to thank you all, and I can take some questions. Okay. Do we have, okay. There is one question. Next slide. Tutorial.
Thank you for presentation.
So yeah, it's sorry to interrupt. The tutorial is not over. We have the hands-on also collab. Yeah. So sorry.
For the ICL few shot and zero shot capabilities that the RT, the relational transformer has, do you think we need retraining after a while for these kind of models? Because the beauty of the ICL is that we need the model can be generalized to unseen data, new data. But sometimes after a while, I think after some downgrade in the results, maybe we need the retraining. Do you think this is true, or have you experienced all these? Not a problem, but a feature. Thank you.
So thank you for your question. I can only speculate here because we haven't really leveraged the power of scaling yet. So I don't think we have reached the plateau where retraining will not benefit a particular model, and then we should only resort to in-context learning or some type of in-context examples in our model. So I think the first step would be to see how much we can benefit for having more data, maybe larger context and larger models in our predictions, and then maybe we can test whether more pre-training helps, or the more we pre-train or the larger the model, maybe that we have reached the plateau. But we are not there yet, I think.
Thank you.
Thank you. That was very interesting. So when you talked about the attention mechanisms, I felt like there was kind of one outlier there where you attend over all the entries of the column. In my mind, that doesn't seem to scale particularly well like the other methods. So I was kind of surprised that kind of the context would stay short in that case. I don't know if that's kind of the right way to capture the distribution, because I think that's essentially what you would try to do with that operation. Any thoughts on that?
Yeah. So, yeah, you are right that all these attention modules do not contribute equally towards the final representation, and we have tried to remove one by one, but it turns out that having all of them produce the best results. Now, in my mind, what you really need to have when you're building such a model is to have somehow a global attention module for sure, and some module which will somehow capture the connectivity information, the structural information of the model. So maybe the two most important parts of the attention would be the global attention plus this neighborhood type of attention. However, as I said, maybe the model is not large enough and the data is not enough in order for a model to be able to learn by itself by looking at data. So the more sophisticated operations we add, the better the performance that we get.
Thank you.
If we don't have any other questions, I think it's time to move on the hands-on part. So what should I do now? Should I somehow click? Should I click?
thanks everyone for staying put until now. We won't be long here, but just wanted to like show a hands-on component so that this is one of the very important takeaways that you can take from this tutorial. We discussed a lot of things, but this is a tutorial where on you can run it on Colab. If you open the link, it was sorry, where was that? Here. Yeah, it says like tinyurl.com/rdl. Yeah, we'll post the link to the chat, and we'll go a walkthrough of this tutorial roughly in three parts. Like we have the first section on how to access databases. We'll use the RelBench, which is the relational deep learning benchmark, to do this. And we'll see different components that a database and tables have. The second section will be, we'll, sorry, yeah, now we can go, yeah. Yeah, the second section will be how can we model the databases as graphs. And there's steps to this. Like one of the key steps there will be how to build node features. And we use PyTorch Frame, which is a multimodal feature encoder. And then how we can build the graph out of the databases by using primary foreign key links. And finally, we'll build the GNN itself, which will have the temporal encoder definition, the GNN definition, and the training and evaluation. So if you want to use RDL for your own custom data sets, this is pretty much the starting point you need end to end. Like you can have the tables defined in RelBench format, and you'll end up with sample visual predictions towards the end. So if we are ready, I'll tell you the instructions how we go. So once you open the link, you can click on the file and save a copy in Drive. This will create your own version of the notebook that will be present in your Google Drive. And Harilaos and Andy will kind of help you to get you on your laptop if, let's say, anyone of you have any trouble in setting up. So raise your hand, and then we can come to you and see if you have any questions or any problem setting up the notebook. But the first step would be like, once you open the link, you click on this option, save a copy of in Drive, and you'll get your own local copy of the notebook, and we can start then. Yeah, so this you can have. I mean, if you have been used to Google Colab, you can say this connect. You can click this. It will connect to a runtime. But let's say if we don't do that explicitly, once we start running the cell, it automatically invokes the connect runtime function. But after you have done the copy, let's try to run the first cell, which will install some of the dependencies. It can take roughly a range of 3 to 5 minutes. So while we are kind of getting started, I would recommend let's run these dependencies installations. It will install PyTorch and its supporting libraries. It will install PyTorch Geometric, which we are trying to base our hands-on development on. PyTorch Frame, which is a multimodal feature encoder for the databases, because you can think like databases have tables which have numerical attributes, categorical attributes, floating point numerical attributes. Some of them can be text attributes, image attributes as well. So we need to encode every one of them into d-dimensional features if we are, let's say, focused on having row-wise node representation learning models. So PyTorch Frame is something that will help us there. RelBench is the library for databases that we are going to use. And this is a collection of 7 databases. We'll see that in detail. And then we'll use transformers and sentence transformers to handle text-based attributes, because in many of the cases we have databases and tables which have certain text attributes. So this will come in handy. But this is like a very minimal requirement of running this, and if you have any questions or any problem in accessing the notebook, you can raise your hand and we'll be on your desk, on your seat. Yeah. But yeah, this is the first cell will take the most of the time because of the training installation, and it's primarily because of the torch, which we have to install certain specific versions so that it doesn't break. If we don't do the first line installation, torch is actually by default integrated or maybe installed in the default environment of Google Colab, but it will install the latest version, and from time to time it can break the other dependencies. So that is kind of taking most of the time. But otherwise, after this after this installation is finished, we can run everything else in a breeze, and we'll try to slowly see the functioning of each of the cells. Yeah, we'll wait for this execution to finish. It shows 2.5 hours, 2.5 minutes. Sorry. Yeah, that's already passed.
Yeah, and then we're happy to take any.
Yeah. Meanwhile, if any one of you have any questions, like feel free. Yeah, we'll keep this part like a bit fluid and flexible. The last 30 minutes, and we can even play with the elements of the notebook. Once we install everything and run the cells, we can get everything running, and we'll end up with a model that can do predictions. But there are a lot of areas here we can play. We'll show some examples as well. Like for example, how can we change certain temporal granularities? I think there was a question on the other side. I'm not sure whether we have that person yet, but there was a very interesting question on how do we fix time granularity? Is there a recipe of that? So we will try to do some experiments on that. But yeah, there are different components in this notebook that we can play with, and this is based on our tutorials in our group's GitHub repository. So you can check out like a lot of the frontier architectures that I was covering, and Laos and Andy. So you can check this out. Yeah, I think we have a question.
Hi, Vijay. I think we've met at Stanford before on the Learning on Graph workshop. My quick question about the 5 different encodings that you mentioned. One of the encoding was temporal, and then there were node features and other things.
Yeah.
I'm curious, the temporal encoding should be more dynamic than the other ones. So would there be a lot of redundancy in the final encodings or embeddings that you get here? And when you add them together, how does that redundancy affect the final embedding?
Okay, so what these encodings are doing are like, let's say I have a node. The first d-dimensional output that I'll get from the torchworm encoder will just inform me in isolation what are the raw attributes that this node has. The second encoding, which I will get as an output of array node embedding, that's taking the integer values of the node type. If let's say I have three node types in my database, which corresponds to 3 different tables. An e-commerce database can have users, transactions, and products. So 0, 1, 2, like integers, will represent the different 3 node types. The output will inform in isolation. The d-dimensional embedding that I get here will inform in isolation the attribute about the node type. Same thing with the distance. Like the distance here is relative, the time here is relative. So in this local subgraph, what is the relative hop distance for each of the nodes corresponding to the seed node? For the time is the same thing. So coming to your question, these are like individual d-dimensional embeddings that's informing a certain specific element of the input data. So in that case, I don't think there will be a redundancy, because this will be something like x equals to x plus something. Like if let's say x is my node feature, then that plus is an additional feature embedding. In original transformer, this is like x equals to x plus positional encoding, like the sinusoidal positional encodings. In graph transformers, we have x equals to x plus graph positional encodings, which is often a function that's computed over the adjacency matrix. But here we have we have elements that we can associate with each of the nodes during the sampling, and these do not require much computation. Like the node type, we already have that available. Hop distance and relative time we can compute in the sampling, and the subgraph we already have it. So we are trying to leverage here the information that we can access very inexpensively during the sampling step, and the encoders are kind of trying to convert them into d-dimensional vectors that we can use them for getting the initial like token representations. Yeah.
Thank you. And how are these encodings added together?
We simply concatenate and do a mixing, but yeah, we can try a bunch of different things. Like in this case, we just do a concatenation and mixing.
Thank you.
Yeah, thanks for the question, and thanks for attending. Yeah, let's see. Okay, so this is finished. I'm sure on your own local, like who are trying to run this should also have been successful. If we don't have very drastic difference in our browser environments, or maybe Collab is not messing up something. So this should be good. We will start with like trying to see if everything works, and this is like a very simple sanity check of importing the libraries which we are using, and then trying to check whether their versions we can access the version help of attribute. If this is successful, then I think we should be ready to go in terms of the libraries. Okay, everything is fine. We have PyTorch, a bit older version, but kind of this version did not break out with the other like PyG based libraries that we are using. So we'll go to the second step, which is we'll check relational databases in RHEL-Bench. So RHEL-Bench, in the oral part of the tutorial, Harilas had mentioned that there are 7 databases. So if we want to access them, we can simply run this dataset module. Inside that, we have a function called get datasets name. And if we run this, we'll see that there are 7 datasets. And if we want to download any of these database, we can simply run the name here. So F1 is downloaded, like it doesn't take much time. It's already downloaded, but if I want to download something else, let's say I want to download a Vito, we just have to run this name, and it will, for the very first usage, it will download from the source repository, and it will cache locally. So for the subsequent users, we don't have to spend much of the time in the downloading. And there are certain data sets. F1 is one of the smallest. This one, let's say it's taking some time, like close to half a minute to 1 minute. But yeah, if the data sets is bigger, for example, Amazon, HM are one of the some of the biggest in this. They can take some time, but still, like they should be like within minutes, like not in hours range. Yeah, so this is a function that can get the data set. Okay, let's wait for this, but we'll roll back to F1 because that was most simpler to proceed with, and also not very big. So we'll actually roll back with F1. I just try to show here the functioning of the get dataset function. But if I do F1 here and run it, we'll see that it won't take much of the time because the data set is already cached, and we can see that it was doing the same for Vito as well. So let's roll back to F1 for the simplicity. We can check the timestamps. So databases here, like we have to kind of, for the purpose of benchmark, we have to have different timestamps for splitting. So we can see that information up to 2005 in the F1 database is used for training, and up to 2010, like from 5 to 10, can be used for validation. And this is what are the chronological breaking points that separates the training, validation, and test samples. When we want to see the data sets, so let's get into the details of the database. We can get the database by simply querying the get_db function, and it returns a database object, which is a custom object defined in the RHELbench library. It has one detail like in terms of like the timestamp leakage. So we can get database without the test timestamp leakage. We can try to run this like a separate argument if let's say we want to access the complete timestamp, but the purpose of but for the purpose of like the benchmark and to prevent the accidental like test set leakage, we have by default the behavior that it will not allow the test set leakage. But anyways, let's go and look at what is present in this data set. So the data set is also the timestamp is also queryable here by using a min and max function. So we can see like it takes if anyone of you is like a Formula One fan, you see that we have the full history of F1, at least the starting point, and the max times, the minimum timestamp is what is showing there. Like we have records from 1950 May, one of the very first races, and if we click this, we can see more details in terms of the schema. So for example, if we go to the database F1 here, we see that it has around 9 rows, sorry, 9 tables. We have races, circuits, drivers, standings, qualifying, and results. And this is a real database, and we'll try to see what some of these tables correspond to in the notebook. But if you look at railbench.stanford.edu, you'll find schemas for all the databases and the list of prediction tasks that is defined. So if you're wondering on what is the kind of prediction task that can be defined on F1, like driver top 3, for example, which we can try to train a GNN for this task. Like for each driver, the task is to predict whether they will qualify for a top 3 in the race in the next 1 month. Like there's a timestamp for each of the tasks. So let's see this driver top 3, for which we'll try to build a GNN model, and we'll see how much our GNN performs in terms of prediction. So coming back to the notebook, we can see like how many tables are there using this table dict attribute, and we can see like all of these tables which I for this for the database for which we saw the schema are present in this database db.table dict and the keys. And if we query individual tables, we can look at the schema. Like the drivers have driver names, codes, the full names, DOB, and nationality. So there are like 7 columns. Some of them are like primary keys. They don't have any foreign key to primary key column, and we can try to query this for some different tables. Let's say races. So we can access the schema of each of the things, each of the tables using these, and you can see that this one has a foreign key to primary key table, and its primary key is race ID, which connects to like it has circuit ID, which is a foreign key that connects to circuits. And if we look at this, like it says the circuit ID is the foreign key to primary key linking. So let's see circuits and double check this. Yeah, so we have circuit IDs. Yeah, so this is how like you'll see there'll be like foreign key to primary key links in different tables, which forms the basis of the graph structure, and the reason why we are spending this like 2.5 to 3 hours today. So I mean, this allows the basis of how the relational deep learning can be executed. So anyways, we can try different tables looking details on our own, and it will return a table object with the data frame that explains the row and column conditioning, or maybe the positioning of each of the tables and the different number of rows. So there's certain metadata here that is a bit detailed, but I will keep just mentioning it. Like there's a data frame which will store all the actual data about the table. They have like primary key column, time column. These are some of the attributes. They have a foreign key to primary key table column. So these are some of the things that are of importance, but they have some other like metadata as well that would be of interest. There are we can run all the standard data frame based functions. For example, if I want to find the maximum or minimum of certain features just for some statistical data analysis purpose before I build a model, everything is supported because of the fact that the table data is built on top of a pandas data frame. So all of that is supported. Going back to the table, we can see there are certain numbers or certain like attributes or cells that can have missing values as well. And I think there's some tutorial day after tomorrow on this topic. So yeah, I mean, it will be great to attend that as well. But yeah, just to show that these are all real data, and then there can be some NaN features and like there's some data which are kind of missing. For example, in the case of times, like milliseconds or other time related attributes, there are a lot of like rows which are missing. So it's like a very realistic reflection that when we have a data in terms of like certain columns versus certain rows, we don't have a dense data, but rather a lot of sparse missing values as well. And we often have to kind of come to a decision how to fill these numbers or how to kind of handle these values. So I'm not going to say like how we handle this here, but yeah, this is just for the sake of information here. Now we can load the task as well by using the get task name functions. In F1 we have 3 tasks. Let's focus on the driver top 3, and then we'll go towards building the model. First building the graph and then the model. So we can get the task by this function, and it will try to download certain task tables for the validation train and test cases separately, and then we'll see that the task table would contain. I'm sorry. Let me actually try to run this. Although it's run, I'll try to run this to show the model training later. Yeah. So the task table will contain the timestamp, which is if you're following what Harilaus was trying to what he was presenting during the introduction, what are the elements that define a task table. So it has timestamp, it has the entity ID, which is the driver ID, and it has the label. So the label is qualifying. It will be 0 or 1 for whether the driver is qualified in the top 3 or not. And we have like around 1353 rows in this top 3 task for F1 drivers. So these are just some of the details there, and we can get the train test. We don't have the labels. It's kind of hidden because of the leakage issues. But if it's needed for some curious purpose, like we can still like get this by running additional argument. So Railbench has nice docs. And the GitHub as well can be exposed, can be explored to see what are some of the things that if you want to build and really go into deep and do some changes, I'll encourage to look into those details. But let's come to the main part. Like how do we model databases as graphs? So we gather first of all everything like the data task and the train tables, and we will set some of the seeds so that we'll not worry about fluctuation if you want to do some comparisons. And we will try to convert the input data that we are getting the databases, like some of the details that we are seeing here earlier. Like they have like you can see there are some numbers which are floating points, some numerical, and some of them can be text as well. Maybe it's not shown here, but it was shown in some of the earlier. Like for example, there's a circuit name, which is a text. So we must embed this somehow. So we use PyTorch frame to do that. And PyTorch frame is a library that kind of implements this under the hood. Like if the raw data frame has different types of input data, it uses their corresponding semantic type encodings. For example, for text, it could be a text based sentence transformer. For numerical, it can be some linear transformation for categorical. It can be a NN dot embedding, like some one hot embedder, and it concatenates that. And then we get, for number of samples, we get NCF, which is N is the number of samples, C is the number of columns, F is the number of feature dimension. And we have to do some interactions to get in embedding of N times D, which is kind of collapsing the column dimension if we are following the formulation that each row should be represented as nodes. So our goal is to convert the raw input data to N times D, and we can do that using PyTorch frame. We see that our databases have different data types. Again, like we have numerical, categorical, text. So this is there's a metadata like call to S types that represents this, and this will be used in the PyTorch frame when we are trying to import the PyTorch library and get the D-dimensional embeddings. So we have to specify the call to S-type sticked when we are trying to make the primary key foreign key graph, and this will underneath call the PyTorch frame. The make primary key foreign key graph is the main implementation of converting the relational databases to relational entity graph. So if you want to understand how this is taking place, I would encourage to look at this library and understand like the implementation of this. But in essence, it kind of materializes most of the introductory things that we covered in the tutorial today, like understand like different tables, their primary key, foreign key links, and then create nodes corresponding to rows. They will have their torch frame representation of the input features. So this is what it materializes, like the make primary key, foreign key graph, and it will store in some cache, and the torch frame is kind of used underneath it, and we have to pass some configuration and some specification of columns, and that should be enough. But most of the things it's happening under the hood. Yeah, let me run this. Yeah, so after this is done, which is here it's trying to download the text transformer weights, like the sentence transformer weights. After this is done, we'll see that our data has been converted to a heterogeneous graph. And if, oh, I missed some of the slides, some of the cells. Yeah, there's, yeah, should be good now. Okay, so this is creating the graph, and some of the graph creation steps may involve processing the text attributes. So this is what the prompt, the output console is showing. And then let's try to see the data. So the data is like a very usual PyTorch geometric graph. If you have worked in the heterogeneous data sets that's present in PyG, you'll see this is a very familiar output. Like it's a heterodata which has different node types. Races is a node type which has features and timestamps. Standings is a node type. Constructor is also, so all of these are node types, and all of these are edges with its standard 2 times E tensor. Like we know that the adjacency matrix or the edge index is what reflects the graph structure of a data in PyG. So these are all the edge types. So this is what we get. Like we get a heterogeneous temporal graph data, and you can see that we can apply most of the things that we know about graph machine learning to relational databases if we are able to obtain this. So we have very simple steps until from part 1 until this part, and then we get a PyG based graph data set, after which we can do very standard GNN stuff, which will be the last part, and I think we should we'll be close to the time as well. But one key thing about the input feature is that they are stored as like TensorFrame elements at first, which is basically saying that it has different columns, like 5 columns, meaning like all of them have separate types, like certain are categorical, numerical, timestamp. Some of them are text embedding based. And during the end-to-end framework, the end-to-end like GNN framework, the learnable parameters in TensorFrame will also get trained. So we can access these like to find out like how many like whether this input raw data are kind of correctly uh, embedded or not. We can see that circuits have like around 7 columns. We have like 3 numerical columns embedding. So by design, like this is multi-model, and PyTorch frame kind of handles that conversion of multi-model raw attributes to d-dimensional embeddings. We have these are some more like helper functions to explore more in the torch frame. We can access these like we can slice these part, and then we can index access all of the torch frame. For example, in the races there was around uh, I think 800 something like rows, so we can access any of the rows individually. We can kind of group them together to have a collection of different rows together. So if I want to slice like 10 rows, we can do that as well. But yeah, and this is like kind of trying to see a specific edge. So this is one edge type that has the edge index corresponding containing source indices and the destination indices. So this is again like trying to see like we have a very nice heterogeneous pyrogeometric based graph. So after this, these things are like common if you are already a seasoned practitioner in graph machine learning. This part is like a cake for you, because like it just tries to define like your neighbor loader, your GNN model, and the general training and test functions. So I'll try to run this, and then we can walk back to some of the things, because the training will also take some time. I think we have a GPU. We don't have a GPU runtime here. For simplicity, we have the CPU runtime. So maybe the training can take 2 or 3 minutes. So I'll run everything, and then we can come back to some of the definitions. But these are simple methods and code that applies in any other graph machine learning workflow. And we can see that we should get our model training. We can see the output console here. Yeah, it's training. So at every epoch, we have 3 different batches of data, 3 different iterations of mini batches. So while it's training, let me show like what we had here. We had a model defined. It used some of the components from RHEL-Bench modeling, but heteroencoder is kind of a torch frame materialization. Heterograph is graph stage wrapped with heteroconv. If you go and look into the RHEL-Bench modeling NN and the heterograph stage, you can see that with few lines of changes, like maybe less than 5 lines of code, you can implement a hetero-GAT, hetero-GCN, or your favorite PyG based GNN model on the same like code base. And then for the other parts, like it has the input feature encoder, the temporal encoder. We have the GNN prediction head, very standard aspects. We can see that the time is added. So this is an implementation of the first like the GNN as RDL baseline. So in that baseline, we had the node features, and the time was kind of added directly. We didn't have any other encoding types. And we can see that the time granularity by default, it takes a day. Yeah, it takes days as the default time granularity. So there were some questions about weeks and months. So we can select that, and maybe you can implement your own temporal encoder. And I think I'll leave to Andy to talk more about this, because he can link to the things, some of the things that he was mentioning. But we can see that the training evaluation is kind of working so far. Wait, yeah. So we see our loss is kind of going down from 54 to 44, 43, 43. And we can, after this is done, like individually, like for every of you, you can try to see some sample predictions and see that whether the driver top three prediction is correct or not. So this is a very simple like notebook that kind of demonstrates all these things. We have some more projects on our group website, like RelGT, Relational Graph Transformer is also implemented. There are a couple of changes on the subsampling and loading, data preparation, and the transformer. But otherwise, most of the things should be the same and build on top of RelBench. So you can check this out as well. After I conclude, I'll open this, but let me see if this has concluded or not. I think it should take roughly like few minutes more, maybe 6-7 minutes more. So I'll just leave it as it is. I will leave the tutorial feedback if you want to put anything on this. Feel free to put your honest thoughts on this and let us know any feedbacks that can help us as well as the organizers who have spent a lot of time and effort to bring this together. And thank you very much. Thank you for the organizers as well.
All right, wonderful. So that brings us to the end of our formal stuff. We have a welcome reception in a second. Oh, sorry, I'm blocking your way. Huh. All right, well, thank you to the tutorial organizers for such a wonderful tutorial. We really enjoyed your tutorial and we had lots of questions, so that's awesome. Please remember to fill out the tutorial feedback form so that we can provide feedback to those who organize the tutorials and us who curated the tutorials to host it at Log. Any comments from the org?
Okay, it's me again. So we will actually have our reception dinner very soon. Probably the food is already out. Well, yes. So probably the food is already outside, just in the area where coffee break is taking place. But if not, it will be there by 6:30. So just in roughly half an hour. And where we can sit, well, we have a lot of beautiful Christmas lights outside. You can either sit in that garden. There's an area, an open space where you can sit. But if you feel like it's so cold for you, then you can sit inside, either here on this side or there are some space upstairs on the second floor. So there are plenty of space here, over there. So for lunches, we use the vouchers over there in our buffet canteen. But for tonight's special reception dinner, I actually ordered some special grill for you. Initially, I was thinking of ordering some Mexican food, but it seems like not everyone is very suitable for that, so I just changed that. But well, if you want to taste something really authentic, here around, you should try Mexican food if you are happy about that. And I'm very happy to see many people already putting on the t-shirts, although it's super cold here. It's very warm compared to many other places. And I hope you will like that. And outside the door, also there's a signature board, which I feel like it can be good for you to take photos for memories, whatever. Yeah. Thank you.